A language model can learn a new task from a few examples without changing a single stored weight. How? This paper offers a theory-first answer. The model is not secretly fine-tuning. It is filtering noisy evidence about a hidden task state. The central claim is that inference-time adaptation can be modeled as online Bayesian state estimation in a low-dimensional space. Its key mechanism is covariance collapse. Informative tokens reduce uncertainty first, and the best task estimate catches up afterward. This is explicitly a theory paper. It derives a probabilistic model and gives minimal sanity check experiments. It does not demonstrate state-of-the-art adaptation on large foundation models. That distinction matters throughout this explanation. Start with frozen base parameters, theta 0. Paper introduces a much smaller latent vector x that describes the task-specific deviation, then maps it into parameter space through a structured matrix B. The base weights remain untouched. The latent task state is allowed to persist and drift. Matrix assesses how yesterday's task state predicts today's, while process noise Q represents non-stationarity or model mismatch. Each token supplies a noisy measurement through an operator H. How does a token become a measurement? Take its negative log likelihood and locally linearize it around the frozen model. The gradient, projected through B, becomes H, the direction in latent adaptation space that this token can reveal. Under Gaussian assumptions, the posterior stays Gaussian. Its mean is the current best estimate of the adaptation state. Its covariance is equally important. It records what the model still does not know and controls how strongly the next token should move the estimate. The Kalman gain balances prior uncertainty against token noise. High uncertainty and clean evidence produce a larger update. Noisy evidence, or an already confident posterior, produces a smaller one. Mean follows the prediction error, while covariance contracts in observed directions. The gain behaves like a learning rate that is derived rather than tuned. It increases when prior uncertainty is large and decreases when the measurement is noisy. As the model becomes certain, adaptation automatically anneals towards zero. Invert covariance to obtain precision. In this information form, each token contributes a positive semidefinite increment. Information literally adds over the prompt, making uncertainty contraction transparent and linking the update to projected Fisher information. The paper's LLM pipeline closes the loop. Prompt tokens enter a frozen forward pass. Token loss creates a local signal. The filter updates the latent posterior, and its mean maps back to an effective low-rank parameter perturbation for the next prediction. Algorithm 1 is the operational recipe. Initialize an adaptation mean and covariance. For every labeled observation, compute the Jacobian, predict covariance with process noise, form the innovation variance and gain, then update both the latent estimate and uncertainty. In implementation terms, the pretrained backbone stays frozen. The only evolving objects are the low-dimensional state and structured covariance. This is still computationally demanding, but it is conceptually different from backpropagating into billions of base parameters. This reframes prompt engineering. Each token is an experiment probing the hidden task. A prompt is informative when its token-level Jacobians cover the latent adaptation directions, not merely when it is longer or more verbose. The observability Gramian sums information across a finite token window, transported through the state dynamics. Uniform observability requires this sum to cover every latent direction by at least alpha. In plain language, the prompt must contain enough diverse evidence to identify the task. Under bounded dynamics and uniform observability, Theorem 1 says the covariance stays positive and bounded, with an upper limit independent of initialization. Informative evidence counteracts uncertainty introduced by state propagation and process noise. Theorem 2 is the paper's centerpiece. Covariance contracts exponentially over observable windows. Rate depends on information accumulation, not on whether the posterior mean has already converged. That separation explains why confidence can stabilize before the exact task estimate. Theorem 3 connects uncertainty to accuracy. Mean square estimation error is bounded by the covariance trace plus a process noise term. As covariance collapses, predictions improve even if the hidden state is not recovered exactly. Now the provocative comparison. Freeze covariance and send measurement noise to zero. The Bayesian mean update becomes a preconditioned gradient step. Gradient descent is therefore recovered as a singular limit that discards uncertainty dynamics. The paper does not claim gradient descent is numerically useless. It claims optimization is an incomplete explanatory model for inference-time learning. Filtering adds measurement noise, uncertainty propagation, automatic annealing, and principled forgetting under drift. A full covariance matrix is impossible at foundation model scale. The proposed route is structure. Diagonal or block-diagonal covariance, low-rank factors aligned with B or ensemble Kalman filters. The paper leaves approximation error and large-scale engineering to future work. The first experiment is synthetic linear regression with a hidden task vector and Gaussian noise. The reported qualitative result is that covariance trace collapses within a few samples before the posterior mean converges, while fixed-step stochastic gradient descent is slower and less stable under noise. The second experiment uses a frozen transformer with a low-rank final layer adaptation subspace and a synthetic logit shift. An extended Kalman filter infers that hidden shift from demonstration tokens. Adaptation stops automatically when covariance collapses, without gradient updates. Appendix approves that in linear regression with zero process noise, this filter is exactly recursive least squares and exactly reproduces the batch Bayesian posterior. The recursion is not a metaphor in that setting, it is algebraically equivalent. Under persistent excitation, the posterior converges almost surely. The appendix also gives logarithmic cumulative regret in the low-data linear setting. These guarantees come from classical Bayesian estimation, not a new theorem about arbitrary transformers. Process noise Q has a useful interpretation, controlled forgetting. With non-zero Q, old evidence gradually loses dominance, allowing the filter to track a changing task. The appendix contrasts this with stochastic gradient descent, which may need a manual learning rate reset after a distribution shift. The caveats are substantial. Deep transformers are nonlinear. Token likelihoods are not truly linear Gaussian measurements, and even structured covariance may be expensive. The experiments are intentionally minimal, and the paper does not show that a real transformer internally executes these equations. Filtering beats fine-tuning offers a precise lens, not a finished replacement for fine-tuning. A prompt becomes a stream of experiments. A hidden task state is inferred, uncertainty controls the update, and informative tokens collapse covariance. Its deepest claim is that learning at inference time may be governed as much by uncertainty as by optimization.